Hey, sorry for the late start. I had traffic on my way home from work and it just backed up for a good half hour. So today I don't really have a goal for the stream, um, but I thought until we get some requests rolling in, um, I'm going to work through some of the math for a robot simulator. Um, so, so here's the situation. If I start drawing it out, we've got a robot with a LiDAR on it, and that LiDAR sees a full 360. And if there's a wall or something, let's see. In the real world, we want it to see all of this stuff. But because of the way LiDAR works, it sees points. So a point there, 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 and they get spread out. Excuse me. And so I want to be able to simulate all of these measurements from there, there, there to there. Like so. And so on. So that we end up with, all of these measurements in one array. But I want to be able to put it into a dynamic environment that changes, and I want it to be able to move around in the environment. So right now it looks like I'm going to have at least 2 classes. I'm going to have a class for the environment. I'm going to have a class for the robot. And because I want to be able to equip this robot with more than one kind of sensor, this one is just a LiDAR, I'm going to have another class that is a sensor, and maybe I'll change how I'm writing this out a little bit. Class environment, class robot, class sensor, and that will be a parent class to class LiDAR. Which inherits from sensor. And so this guy is going to have read, which means this guy will inherit read, but this guy will override read. Override read. This guy will belong to, or will possess, a list of sensors. It will also belong to an environment. I'm going to cheat a little bit because I've already done this a little Nope. Robot belongs to an environment. Though I'm not sure that's necessarily the best way to do it. This guy will also have an update. Function. And that function will take in a delta time. This guy will have an update function, which will take a delta time. This guy will have a draw function. Draw. And it will take a surface. This guy will take a draw function. And I don't know if those will take draw function or have a draw function yet, but we'll see. So as it is, I have to write this guy's read. So how are we going to do that? Well, the way I want to do the environment, because this sensor interacts with the environment, I want this guy to have a bunch of walls, because that's essentially what all these white parts are. Those are just walls. And since I want that to be drawn dynamically without me having to recode things, I would like that to be done via a configuration file. And I think I want to do that with JSON. So I'll have a JSON object read into this guy, which will create a bunch of walls, and then the sensor will interact with the walls. So this guy will have a you're going to have walls. And that's going to be a dictionary. This guy. Dictionary? It's going to be list of dictionaries. I think is the way I want to do that. And so the way I want to do read, this guy is going to iterate over the list of walls and project the point onto the wall and figure out where that point is. So for each wall, let's change colors. For wall in walls, and this is going to be find ray wall intersection. Which sounds easy, and it is, but it's not quite what you would think. Because once I find the ray wall intersection, I have to verify one, the wall is in front of the sensor. Front of sensor. And then verify 2, that the, or not the wall, but the point verify that the point is in front of the sensor, and then verify that the point is on the wall. And you're probably looking at this going, well, by definition, doesn't this intersection thing mean that both of those are true? And if the walls were infinite length, yes, it would. However, we don't have that guarantee. If we break this down a little bit, and we're going to look at just one ray cast from this LiDAR to the wall. Boom. Let's put a doorway there. This wall doesn't exist over here, right? Over here. This is an empty space in the wall. But if I were to treat this, can I do this? As one solid line, even though it doesn't exist here. It would see this point of intersection, and if we don't bother doing all the checks, we should be good, right? But if we found a point over here, this point doesn't actually exist, even though it lies in the same line. So we want to keep this one, keep that point, filter out this point. Now, normally, to find this intersection, we would say, this line equals, there is sum y equals mx plus b. And this line equals, or is y equals ax plus c. And then you would set them equal. Solve for x. And then solve for y. And that would be your intersection point. But I need to verify that this point, xy, is in front of the sensor and not in the doorway. Which doesn't sound like it would be difficult to do, but you have to remember, I'm also ultimately reporting the range. So how long is this piece? Because that's what the LiDAR is going to give back. So there's actually an easier way for us to do this, and it's using parametric equations instead of these nice Cartesian ones. And that's, so if we remember that the way we're defining our walls, which I don't think I said outright, but if we can get that equation, we've got the points, right? So I'm going to represent the wall this way. Line segment there, line segment there, line segment here, and I have the start and end points, and then I have the robot, and I have my rays that I'm casting. And I want that to keep going. But it's likely going to do that. So if we're just comparing against this piece that I will highlight in green, if we're just dealing with this wall piece, for the sake of thinking through our algorithm, we want to know what is this angle. And nope. Good enough. We want to know what our angle is. And let's get the right color. Theta 2. Theta 1. So that we can calculate this line. And we want to know, where is it? There it is. We want to know this x1, y1, and x2, y2. Why are we going to do these in different ways? Why this one with thetas, why this one with points? Because when I'm defining my line in the JSON file, it's easy to do that with points. And convenient to do it with points. When I'm going to calculate my LiDAR stuff, it's actually really convenient to do it with angles. So why not just make our lives easier and choose the easy ways? Now we can represent our line here as x equal to I'm going to back up a little bit. Because we're dealing with computer graphics here, I'll draw the coordinate system because it's not what you're used to seeing. X, Y. So I've drawn the positive X and Y. So the further positive we go in the Y-axis, the further down the screen we go. Positive X means further right. It's a little bit confusing, but you can get used to it. Normally what I do is I just do it the way I think it should be done and then add negatives in there until it works. Which is not the correct way to do things, but it does work. Bothering me that that point's not in the right place. Okay. Now with that in mind, we're going to do x equal to the cosine. I think it's cosine. Pick the correct color. Cosine of theta 1 times some range plus, this is going to be x robot, y robot, x robot. And y is going to be, actually, is cosine correct? Cosine is not correct. This needs to be sine. Because this is our angle, this is our hypotenuse, this is adjacent, and this is opposite. And we want the length of this opposite side. So since cosine is opposite over hypotenuse, no, sine is opposite over hypotenuse. We need sine. And then since y is 90 degrees off of x, we're going to use cosine theta 1 times r plus yr. So r is the range. And I'm going to do this generally and get rid of the ones because it's the same equation for the other line. We're just talking about a different theta. Now we got to do the green part. This one also we need to represent parametrically so that we can intersect them properly. So we'll do x equals x2 minus x1 times x plus x1. Y equals y2 minus y1 times y, not y, and not x. We'll call it t plus y. Y. I can't stop hitting buttons. Y1. YT, why not R? It's because R is the range from the robot to the wall, and T is the ratio of the wall. So by doing it this way, if T is less than 0, if it's negative, then we hit somewhere out here. If T is somewhere positive, it's on the right side of the base point of the wall. If it's greater than 1, it's outside the length of the wall. If it's between 0 and 1, then we're in the right range. We have actually hit our target section of the wall. And then we can just check R, and if R is greater than 0, it's not negative, so it's not behind us, then we're in the right place and we found the right one. So then our test criteria, all right. R is greater than 0, and 0 is less than T is less than 1. Those are the points we care about. Now, intersecting these is fairly straightforward. We can do that with standard algebra, which we can then later turn that into linear algebra. So we have x equals x2 minus x1 times t plus x1, and we have x equals sine theta times r plus xr so then we have is this the way to do it? Yeah. Well, I mean, yeah, we'll do it this way for now. So we have no, I'll go ahead and show you the linear algebra way. I was going to work it out with regular algebra, but it gets confusing to look at if you do it that way. So we'll go ahead and write out the formal equations. Times t plus y1 y equals cosine theta times r plus yr. Now, with that, we can form our linear algebra equations. So we'll say point P, which is what those points are, point P is equal to the slope, so we'll do this one first. So it's equal to, yeah, sine theta and cosine theta? Yeah. Sine theta, cosine theta, times r plus xr yr. P is also equal to nope, x2 minus x1 y2 minus y1 times t plus x1 y1. Then we can set these two equations equal, and we're left with sine theta cosine theta times r plus xr yr which is lovely. And then we will do some math. We'll subtract this part from both sides, and we'll subtract this part from both sides, which will give us sine theta cosine theta times r minus x2 minus x1 over y2 minus y1 times t equal to x1 y1 minus xr yr. And now this can be rewritten if we use the vector form and turn that into a matrix. So then we'll have, remember this is equivalent, sine, sine theta cosine theta, and this will be x2 minus x1 y2 minus y1, and this is going to be times vector r and negative t. I think I've written that correctly. Yes, pretty sure. And then this is just vector, or yeah, just the addition of vectors, or subtraction. So we can do x1 minus xr and y1 minus yr. So when you do all that math out, you end up with r and t. How do we get to just r and t? Because those are the ones we're interested in. Well, if you remember from when we did, or if you didn't, even if you, bleh, if you were here and saw when we did passive ranging, or indoor localization, we used a technique called the pseudo inverse, which we write this way. So a pseudo inverse equals a times a transpose inverse times a transpose. Nope. A transpose A. And that, and we will apply this, the pseudo inverse thing, to this matrix. So we'll have R and negative T equals, sine theta x2 minus x1 cosine theta y2 minus y1 pseudo inverse times x1 minus xr y1 minus yr. And this is the formula that we use for doing the ranging part. And then we just apply our test logic that we did up here to find out if it's a valid point or not. And then we'll just iterate this over all of the different walls. Probably not the most efficient way to do it, but it works. I've tested it. And if we want to see the code itself, here and here, ta-da, this is the test, and it does function, I believe. Yeah, I believe I can run it and show you what it's doing. Oh no. Ah, I see. There. There and there. I took out the debug stuff. So this is it working. All the cyan points, which may be a little bit hard for you to see, but I think you can see it. All the cyan points are its measurements. And these ones that are kind of hanging out here, let me make it a different color so it's easier for you to see. And I'm going to take that out. Blue, green, red. There we go. That's probably a little better. All of these points that are hanging out here that aren't on a wall are because hey, thanks for watching. These are hanging out because I set a maximum range. So to answer your question, it is college level math, but it's not that hard. You can probably do this after... You could probably do it in 10th grade, depending on what algebra you use. Some algebras will go over matrix stuff. Some of them won't. It just depends. But yeah, this is... And I did all of this in Python. So my end goal is to end up turning this algorithm. Well, the algorithm works fine. Instead of using OpenCV to display it like I was just doing, I intend to create a Pygame API so that somebody can just load it up and say, I want to override the robot.update function, and all of your robot control logic will go in the robot update function. And so your entire robot control scheme will sit in that, and my stuff will take care of running the simulation, so that it's the end user doesn't have to know anything about how the LiDAR ranger works. You can just say, I need my LiDAR data, and this is what I want to do with it. We'll see how well that works, but that's my goal. I haven't had any requests. Let me check the Discord. No requests here. All right, so I know it was a little bit shorter than normal, mostly because we got a late start, but I think we're going to call that good for now. So if you did enjoy what you saw here, if it looked interesting, or if you really want to see more of this robot simulator, be sure to hit that like button. Let me know in the comments below. Join the Discord. If you have suggestions for this, maybe mention those there. I love to work math problems just in general. So if you have a homework problem that you're having trouble with, if you want me to work an example problem or go over a homework problem, I'll change the numbers up and work it so that you can see what the process is. Pop those questions in my Discord. Put them in the YouTube chat if you feel the need, if you can during a stream, and I'll be happy to work them. Subscribe if you think this will be helpful to you, and we'll see you guys next week.